Hello and welcome back. In this section, we will continue our discussion of entropy, and we will look at examples of how to calculate the integral that expresses the change in entropy in a number of cases, and start looking at the relationship between, or start looking at how the direction in which the entropy increases is consistent with our sense, with our physical intuitive sense of increase in disorder. But before we get going, I should point out that some people might find the derivation we went through the other day a little bit lacking in completeness and a little bit not entirely satisfactory for how we obtained our central result, namely that the integral going from state 1 to state 2 of dq reversible over temperature is independent of which reversible path links state 1 to state 2. Some persons might find that our derivation, the last few steps of our derivation of this key foundationally important result might be not entirely satisfactory or not completely rigorous to their taste or satisfaction. For such persons, if people would like to see a more rigorous, completely mathematically respectable and completely correct derivation of this result based on everything else we have talked about the second law of thermodynamics, the Carnot engine, the Carnot cycle, what have you, you could turn to our lecture notes and you will find in the appendix, because at the end of the lecture notes there is a couple of appendices, additional material. Appendix B, page B1, it says the second law, Carnot cycles and entropy, an alternate approach. Page B1, another approach that leads from consideration of the Carnot cycle to entropy. Pages B1 to B14 in this final section of the lecture notes. This is not something I expect everybody to work through. This is just for those who are really mathematically curious and want to see a more rigorous, completely correct derivation of the result we talked about. That is in this section of the lecture notes, just for further reading for those who might want to see the same derivation, the same result obtained in a completely mathematically careful, more careful way. So that is there, but it is not strictly necessary for purposes of this class. So this, to begin where we left off the other day, this tells us that there is a function of state called to which we attach the name entropy, and we define delta S, the change in entropy. Remember, delta of anything is the change in that quantity. So we define the change in entropy define the entropy, give it the symbol S, capital S, such that delta S, change in entropy in going from state 1 to state 2, is defined as, well, of course it's S in state 2 minus S in state 1, but it's defined as the integral going from 1 to 2 of dq subscript reversible over T along any reversible path linking state 1 to state 2. These are quotation marks. And what we have shown so far is that this quantity, defined like so, delta S going from 1 to 2 depends only on the states 1 and the states 2 and is independent of the path. That tells us this quantity S, entropy underlying this, is a function only of which state the system is in, because only if the function S depends only on the states 1 and 2 is it possible that the difference between states 1 and 2 is independent of the path that connects us, that takes us from 1 to 2. Anyway, that all said, how do we actually go about calculating this? How do we actually calculate a number, a numerical value for this integral for various processes of interest? Let's start looking at a whole set of processes that are of interest to us and for which we might want to calculate the change in entropy. Okay. First off, units. Delta S is the integral 1 to 2, initial to final state, dq reversible over temperature. Units. dq reversible, heat has units of joules, temperature is in Kelvin, this is always absolute temperature. So 1 over temperature is units of Kelvin, joules per Kelvin. Joules per Kelvin. These are the units of entropy. If delta S has units of joules per Kelvin, then S also has the same units. So S units are joules per Kelvin for the entropy. Okay. Let's see. Examples. Heating at constant pressure. Let's say we take a sample of ideal gas, because that's simple to work with, or a sample of water, doesn't have to be ideal gas. Water, a chunk of iron, and we heat it, raise its temperature, supply heat, raising its temperature, keeping the pressure fixed at every point. What's going to be delta S? So let's say we start at pressure P, temperature T1, that's the initial state, and by supplying heat we raise its temperature to temperature T2. Keep the pressure fixed at pressure P, that's a comma, pressure fixed, raise the temperature from T1 to T2. How do we go about calculating delta S? Because this is a very common thing. We want to know how much the entropy changes, let's say, when we change the temperature holding the pressure fixed. The way we do this is we start with the definition. Delta S is what? Integral from 1 to 2 dq reversible over temperature. So we start with this and ask ourselves, what can we say about this? So what's the heat transferred to raise the temperature from T1 to T2 every step along the way? Delta Q reversible, because we are raising the temperature bit by bit, keeping it in equilibrium, but we are keeping the pressure fixed, and remember that is simply number of moles of the material multiplying Cp per mole multiplying delta T. What was the heat capacity at fixed pressure per mole? It was simply the heat transferred per mole to raise the temperature by an increment when the pressure is fixed. So we use this to plug in here. Okay? So this integral becomes something that looks less unfamiliar, less daunting, and that becomes the integral from state 1 to state 2, number of moles Cp per mole dt over T. Let's say the heat capacity is independent of temperature. For an ideal gas, we had Cp per mole was 5/2 R, R being the gas constant. For other materials, Cp per mole can depend weakly on temperature, weakly or strongly, I should not say weakly or strongly, if it's independent of temperature. We can pull number of moles outside, Cp per mole outside, we get integral from the initial state to the final state dt over T. This is if Cp per mole is weakly temperature dependent. But that's an integral we know how to do. So that becomes number of moles Cp per mole natural logarithm of T final over T initial. And let's check the units. N is number of moles, Cp per mole is joules per Kelvin per mole. These cancel out, so the units are joules per Kelvin, as they should be. Okay, so that's the delta S for heating something at constant pressure. How about at constant volume? Well, let's look at that. Delta S integral from 1 to 2 dq, always go back to the definition when in doubt, dq reversible over T. Under constant volume heating conditions, this becomes 1 to 2 number of moles Cv per mole, which might depend on temperature, dt over T. And that becomes number of moles Cv per mole natural logarithm of T2 over T1 if Cv per mole is independent of temperature, or if we neglect the temperature dependence of Cv per mole, as we can if we are using the ideal gas as an example, or in very many other cases. Okay. So we have looked at this pair of examples. What if there is a change of phase or a change of state? I want to work through this slowly and carefully. Oh, actually, before I even look at that, delta S we saw was Ncp per mole logarithm T2 over T1, or Ncv per mole logarithm of T2 over T1 for heating, where all we are doing is changing the temperature. All we've done is raise the temperature T1 to T2. If T2 is larger than T1, then that implies T2 divided by T1 is greater than 1, and that implies the logarithm of T2 over T1 is positive. Right? Logarithm of quantity greater than 1 is positive, that's positive, heat capacities are positive, implies delta S is positive. Or the entropy in state 2 is larger than the entropy in state 1. Lo and behold, as the temperature rises, the entropy goes up. But that's what we expect. Our natural sense is that as we raise the temperature, the disorder is higher. And yes, at the higher temperature, S2 is greater than S1, so the state at the higher temperature has the higher entropy, consistent with our intuitive notion that disorder is greater as the temperature is higher. Okay, now let's look at change of state, change of phase. And I should pick a specific example. Say we start with H2O, solid, ice, at pressure of 1 atmosphere at the normal melting point, temperature of 0 degrees C, which is 273 Kelvin. Supply heat at fixed pressure until we get H2O liquid. Liquid, again at 1 atmosphere and 0 degrees C, 273 Kelvin. Where we heat this, keeping the pressure fixed, temperature is fixed. What's happening is it's absorbing the latent heat of fusion, the latent heat of melting, and turning from ice at 0 degrees C to liquid water at 0 degrees C. That's all that is happening here. What is delta S for this? Delta S. And let's say we have 1 mole of ice. Delta S per mole for fusion. Why for fusion? Because that's the process, melting. Delta S per mole, say 1 mole of H2O. Let's calculate the change in entropy for the H2O, the 1 mole of H2O that we have here, due to this change of fusion, which remember is the same thing as melting. Again, we go back to the definition, state 1 to state 2, dq reversible over temperature. Okay. During this process, the temperature is fixed. It's at 0 degrees C, it's absorbing heat from the environment with no change in its temperature. So we can pull the 1 over temperature outside. 1 over temperature, and what's the temperature? It's the melting point, TMP for melting point. That came out of the integral, because we still have 1 to 2 dq reversible, because the temperature got, we could bring out, so bring in front of the integral. Okay, adding up dq reversible, that's simply the total heat transfer reversible under conditions of fixed pressure. Remember, we are keeping the pressure fixed, divided by T melting point. The pressure was 1 atmosphere, constant pressure. Q, total heat transferred reversibly, the pressure has been held fixed. But that is simply the delta H, heat transferred under fixed pressure conditions is delta H, you might remember, delta change in enthalpy. So that's delta H per mole for fusion of H2O divided by T melting point. Units, delta H has units of energy, say joules, T melting point is in Kelvin, so it's in units of joules per Kelvin. For water, I happen to remember this number off the top of my head, delta S molar fusion for H2O, the delta H molar of fusion is roughly 6.01 kilojoules. For H2O, delta H molar fusion for H2O is roughly 6.01 kilojoules per mole times 10 to the power 3 joules per mole. Temperature melting point is 273 Kelvin, and that is going to be what? Plus 22. That's plus 22 joules per Kelvin per mole of water that's melted. Plus sign. That tells us that the liquid, remember state 1 was the solid, was the crystal, was ice. State 2 is the liquid. Ice, crystal, liquid. Going from state 1 to state 2, upon melting, the entropy went up. The liquid has a higher entropy per mole than the crystal, and yes, this is consistent with our expectation that a liquid is a more disordered state than a crystal. So it's consistent with what we would have expected. How about for boiling or vaporization? Same argument. Delta S per mole, let's say for vaporization of H2O. It's worth working through this more than once. 1 to 2, state 1 to state 2, dq reversible over temperature. At the boiling point, what's going on? What's taking place? H2O liquid at 1 atmosphere, and at an atmosphere that's going to be 100 degrees C or 373 Kelvin, turning into H2O in the gas phase or in the vapor phase again at 1 atmosphere and the same temperature. That's the vaporization or boiling process. 1 divided by T, that's now the boiling point temperature. T BP, that's the boiling point temperature. Multiplying integral, going from 100% in the liquid phase to 100% in the vapor phase, dq reversible. And that becomes the total heat transferred divided by the temperature at the boiling point, TBP, Q reversible. Again, pressure is fixed. We are boiling the liquid at a fixed pressure, and that per mole becomes delta H per mole vaporization H2O over the boiling point. What allows us to identify the heat transfer with the delta H is the fact that it's taking place at a fixed pressure. That's what enables this step. And that is delta S per mole vaporization for H2O. At 1 atmosphere pressure and 100 degrees C, I just happen to know this number off the top of my head. I don't expect anybody to memorize these numbers. Delta H per mole for vaporization of H2O is approximately 41 kilojoules per mole. I just happen to know this number. So delta S per mole for vaporization for H2O under a pressure of 1 atmosphere, because when you say it's a pressure of 1 atmosphere, that automatically tells you the boiling point at 1 atmosphere is 100 degrees C. That is going to be 41 times 10 raised to the power 3 joules per mole divided by the temperature, which is 373 Kelvin, and let's see what that works out to be. Roughly, approximately 110 joules per Kelvin per mole. And again, plus sign. So the vapor has a larger entropy than the liquid. This is the change in entropy per mole of water when we go from the liquid phase to the vapor phase at 1 atmosphere and 100 degrees C. Pressure is constant, temperature is constant, all that has happened is there is a change of state. So just for changing from the liquid to the vapor at a fixed pressure and a fixed temperature, lo and behold, the entropy went up by 110 joules per Kelvin per mole. And yes, we expect the vapor to be a more disordered, more disorganized state than the liquid. That's very similar to what we had here for the change in state here. This is for going from H2O, solid crystalline ice, at 1 atmosphere and 0 degrees C to liquid water, again at 1 atmosphere, 0 degrees C. No change in temperature. This is just associated with the change in state of matter at a fixed temperature. The crystal went to the liquid, no change in temperature, we got an increase in entropy, reflecting the greater disorder of the liquid as compared to the crystal. Here, when we went from the liquid to the vapor, we see similarly a large increase in entropy associated with the change in disorder just in going from the liquid state to the vapor state at the same at a fixed temperature and pressure. This is a significantly large, quite a large number, and that comes from two places. There are two reasons we have this large increase in entropy in vaporizing water in particular. One has to do with the increase in volume, because the vapor occupies a volume per mole at this pressure and temperature roughly 2,000 times, I think about roughly 17 or 1800 times the volume of the liquid, because the vapor is much less dense. The volume expands enormously. That leads to disorder. The other thing is we are breaking up what is left of the hydrogen bond network in the liquid at 100 degrees C. So liquid water still has a fair degree of hydrogen bond network, which imposes some level of order, structure, some level of structure on the liquid. That is destroyed, completely gone mostly in the vapor phase, and that destruction of order, that loss in structure that is imposed by the hydrogen bonds that remain in the liquid phase, that contributes a large fraction to this entropy increase upon boiling. So we have looked at, to look in the lecture notes, we have looked at delta S for phase transitions at equilibrium, coexistence curves, which are simply combinations of pressure and temperature where different states of matter can coexist, melting of ice at 0 degrees C, vaporization of water, H2O going from the liquid to the vapor, that gives us this result on page 52 for the delta S molar vaporization. Reversible adiabatic processes, we will come back to this the next day in the next section. Delta S is 0 for these. We will look at that again. Isothermal reversible expansion. We have not yet come to this, but we have looked at, in this section, we have looked at what's on page 53, heating at constant volume. dq reversible is written like so in terms of CV per mole. We have looked at this. Heating at constant pressure, we simply have Cp per mole instead of Cv per mole. We have gone through this, so we have looked at this. Next day, where we will start again, is looking at this situation of an isothermal reversible expansion where we keep the temperature fixed, increase the volume. Because what we have looked at is when we keep the volume fixed, raise the temperature. That was heating at constant volume. The counterpoint is keeping the temperature fixed and changing the volume. We need to look at that separately the next day, and that will be the subject of our next section. Once we have gone through all of these, we will have made significant progress in terms of, remember what I was saying, we need to learn how to use a hammer, how to use a wrench, how to use a screwdriver, how to use these different tools. We are making rapid and considerable progress. We will have made significant advancement towards building, I would say, 2/3 or 3/4 of all the instruments we are going to need. And from there on, we will be looking at applying what we have built to a plethora of situations and problems of physico-chemical interest as we go forwards. But that will be a subject for the next day. That is all for this section. We will start looking at this in separately the next day. Thank you very much for your focused attention today. Thank you. We'll look forward to seeing you next time.